So we're going to talk about math induction today. Our objective is to prove using math induction. You can follow the slides here at the beginning. One squared, 2 squared, 3 squared, 4 squared, and 5 squared. So the sum of the first n odd numbers is n squared. So then to say this is conjecture true, we must prove it. And a proof is a clear argument that demonstrates the truth of a statement beyond a doubt. So the principle of math induction, for each natural number n, everybody knows what the natural numbers are, right? 1, 2, 3, 4, they're the counting numbers. Those are natural numbers. We let Pn be a statement depending on n. Suppose the following two conditions are satisfied. P to where you plug in 1 for n, P to the 1 is true. For every natural number k, if P to the k is true, then we know that P to the k plus 1 is true. Then Pn is true for all n natural numbers. So to apply this principle, there are two steps. First, we have to prove that P1 is true. And then the second step, we assume that Pk is true and use this assumption to prove that Pk plus 1 is true. Notice that in step 2, we do not prove that Pk is true. We only show that if Pk is true, Pk plus 1 is also true. So there's sort of an assumption that Pk is true. The assumption that Pk is true is called the induction hypothesis. And then you've got a little cartoon there in the notes. So if he's on rung K, then it'd be easy to get to the next rung. But then if that's true, you could climb the whole ladder. So you have to reach the first rung to begin with. So to do a proof by math induction, we're going to prove for all natural numbers n that 1 plus 3 plus 5 plus 2n minus 1 equals n squared. The solution, we're going to let Pn denote the statement 1 plus 3 plus 5 plus 2n minus 1 equals n squared. We need to show that P1 is true. But P1 is simply the statement that 1 equals 1 squared, which of course is true. So we've shown that P1 is true. I take the first number in the sequence, 1, and then I plug in it's the term number n. 1 squared is 1, so 1 equals 1. So the P1 is true. Now we assume Pk is true. Thus our induction hypothesis is we change all the n's to k's. We're going to say that that's true. We want to use this to show that Pk plus 1 is true. That is 1 plus 3 plus 5 plus 2k minus 1 plus 2 times k plus 1 minus 1. We're plugging in k plus 1 for k in the previous statement equals k plus 1 squared. So everywhere in this statement we plugged in, wherever there was a k, we plugged in k plus 1, and then we added a term here. We added the term in the sequence prior to this one, which is 2k minus 1. We note that we get Pk plus 1 by substituting k plus 1 for each n in the statement Pn. We start with the left side and use the induction hypothesis to obtain the right side. of the equation. All right. So here's how it works. We've plugged in the k plus 1 for k, and then we group the first k terms. That was our original statement. Since we knew from on the previous page, we knew that what's in the red brackets, we knew that equaled k squared. That was our original statement. So the induction step is to replace what's in the red brackets with k squared. Then I have my k plus 1 term next. And then I simplify that, and I get k plus 1 squared. Thus, pk plus 1 follows from pk, and this completes the induction step. Having proved steps 1 and 2, we conclude by the principle of mathematics induction that p to the n is true for all natural numbers n. Now, it probably doesn't make a whole lot of sense right now. You may kind of see the process, but we'll do a couple examples. Once we do the examples, then it's more clear what we're trying to do here. All right, so let's look at our examples. Proof by mathematical induction. We need to prove that for every natural number n, 1 plus 2 plus 3 plus n equals n times n plus 1 divided by 2. So the solution, we're going to let Pn be the statement, the original statement, and we're going to show that Pn is true for all natural numbers n. We need to show that P1 is true. Don't forget this step. We have to show P1 is true. So wherever there's an n in this equation, wherever there's an n, we plug in 1. And the first term is 1, right? So the p to 1, we would have 1 here, and then we plug in 1 for n, and we show that that is 1 does equal 1 over 1 plus 1 times 1, which is 1, right? That equals 2 over 2, which is 1. So P1 is true. You've done that. So now we're going to assume PK is true. Thus our induction hypothesis is we replace all the n's with k's. We're going to assume that this statement is true. And then we rewrite this statement in the box. But wherever there's a k, we're plugging in k plus 1. And then we're adding this extra term of k. You know, this we're not adding it, we're showing it. We're showing not only the last term in the sequence, the k plus 1, but the one prior to it, which happens to be the k. So then, you know, we plug in k plus 1 wherever there was a k, and then I'm going to group this right here, and that's where I'm going to plug this in for that. That's the induction hypothesis. So what that looks like is did I go? Okay, yeah. So we group the first k terms. So I'm just working with the left side now. I'm working with the left side. We group the first k term. So you take that last statement from up above, and we are taking, we've got, we group the first k term, so it'd be 1 plus 2 plus 3 plus ... plus k. We group that, then plus k plus 1. Then what's in the brackets, up above, two statements above, if you look back on that page, two statements and above, we said that equaled k times k plus 1 over 2. So I replace it. That's the induction step. So I replace it. It becomes k times k plus 1 over 2 plus, and then I take this k plus 1 right here. It's right here. I plus k plus 1. Alright, then we're going to factor. What can I factor out of this statement, the induction hypothesis? What can I factor out? Yeah, we factor out k plus 1, and I'm left with k over 2 plus 1. Alright, so then for that second parenthesis, we got to get a common denominator, so we would get k plus 1 times k plus 2 over 2 is the common denominator. And then we have, so that's going to be k plus 1, we just kind of changed the way it's written, times k plus 1, oh, not 11, plus 1, k plus 1, plus 1, k plus, let's erase this here. That's times k plus 1 plus 1 all divided by 2. And that's what, if you look back up to the last printed statement, that's what we said the left side equaled, right? So there we've proven it by induction. We've proven that k plus 1 is true. Yes.
In step 2, I'm wondering, like how do you get the 1? Because I see how you distribute and like factor like the k plus 1 times k plus 1 part, but I don't understand this one.
Right here? This part, this right here?
The previous line.
This line? How you get the 1?
No, this step right here.
In the printed part? Well, let's go back up there. How you get the plus 1? Okay, because right here I plug in, for here I plugged in k plus 1, right? And then for the second k, I plug in k plus 1. And then I have to add 1 to that. Right? It was already there. It didn't come out of air, it was already there. Alright? Okay. Alright. Now let's go through the whole process. So, the first thing you need to do, and you need to have all these steps when you do math induction. If you don't have the P1, it's a deduction. So we've got P1. We're going to show this is true for P1. So P1, we've got, this is the first term, so that's 1 squared is going to equal, and then I take this, and wherever there's an n, I'm going to plug in 1. So it would be 1 plus 1 plus 1 times 2 times 1 plus 1 enclosed all over 6. So that's going to be 1 times 2 times 3, which is over 6, which is equal to 6 over 6. And that's 1. 1 squared equals 1. So we've proven, which equals 1. So we've proven P1. P1 works. Okay? Now we have to show that PK plus 1 is true. So the first thing we do is pk. Wherever it's that step is simply wherever there's an n, you plug in k. You have to do that step because that's just the way it's taught. They changed the n from natural number to k. All right, so it's a reiteration of the first part, but we're changing everything to k. If you go through and you do it all as n, then I won't count it right. All right, that's just the way they do it. That's the way our pre-cal will do it, calculus, and that's the way IU does it. IU even wants us to teach it this way. So this is how you need to be able to do it. So you plug in k, so we would have, I just take the original statement, I've got 1 squared plus 2 squared plus 3 squared plus dot 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 k squared equals k times k plus 1 times 2k plus 1 all over 6. Right? Now we have to show pk plus 1 is true. So pk plus 1 would look like this. We would have 1 squared plus 2 squared plus 3 squared plus k squared plus k plus 1 squared, and that's going to equal, that equals, wherever there was a k, I plug in a k plus 1, so that would be, I'm going to plug in k plus 1 here, here, and here, wherever there's a yellow mark, right? So that's going to be, that would be k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 in bracket all over 6. Right? So now we are going to group, right? So I'm going to take this left side and I'm going to group the first part. So we've got 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared plus k plus 1 squared, and I group the first part. That equals to, okay, then let's simplify the right side. We can simplify that to k plus 1 times k plus 2 times 2k. If I distribute the 2 to the 1 up above, that's 2, then we add 1, so 2k plus 3 all over 6. All right. Everybody with me? Everybody got it? Now, here's the key step, the induction step. What I'm going to do in the next step is I'm going to take what's right here. I'm taking this. That's pk. And I know that this statement right here equals what's in the blue. So I'm going to take what I have in the brackets down here. I'm going to replace it with that. That's the induction step, where you're assuming pk is true. So I take that and I replace it with this. So I'll have all that will be replaced. The only thing that remains is this part right here. That still is unique to the left side. Alright, so what that step looks like, if I do that step, I will have, since we have the right side simplified, we're just going to assume it's the same all the way down. It's k plus 1 times k plus 2 times 2k plus 3 divided by 6. We won't rewrite that every time. But what I'm going to do the induction step so it would look like the next step would be, when we plug that in, we have k times k plus 1 times 2k plus 1 divided by 6 plus k plus 1 squared. That's the left side when I plug in the pk. This right here, this part right here was plugged in. That's the induction step. I substituted it for 1 squared plus 2 squared plus 3 squared plus plus k squared. So now, and then that equals the right side, which we already had simplified. So we have to make this look like the right side. So we start to simplify. The first thing I would do is get the common denominator with this last part. So we have our next step. We would have k times k plus 1 times 2k plus 1 plus and then we're going to put all of it over 6, and then if I put the last part, so there'd be 6 times k plus 1 squared, right? To get this have a common denominator, I multiply the top and the bottom by 6. So that's what I've done there. Everybody understand that step? Any questions? No questions, okay? So then we simplify further. What can I factor out? On the top line, what could I factor out? So you have to do some factoring here. What can I take out of that? Yes. Right, we factor out k plus 1. So we take the k plus 1 out. So we have k plus 1, we factor it out, and then we have, we're left with brackets here, k times 2k plus 1 in bracket plus 6 times k plus 1 closed bracket all over 6. Right? Now we're going to simplify what's in this bracket. Would be my next step. I want to make sure everybody's got this. So now, when you're doing this factoring, remember, we know what the right side. On your paper, you can look up at what the right side is. You can see, if you're having trouble factoring, look for the different factors. K plus 1 is one of the final things that the right side has. So it makes sense to factor that out, right? So then let's go ahead and simplify what's in the brackets. So we've got k plus 1 times brackets. We've got 2k squared plus k plus 6k plus 6 in brackets all over 6, right? Then we combine like terms, so we would have k plus 1 times, in the brackets, we would have 2k squared plus 7k plus 6, close bracket, all over 6, right? And then we have to factor 2k squared plus 7k plus 6. So, you can probably figure out how to factor that, but again, use the right side to help you, right? The right side, the rest of the right side after k plus 1 has to be k plus 2 times 2k plus 3. Is that the factor of 2k squared plus 7k plus 6? Well, you can either factor it and try it, or you can test it. We could do the FOIL on. So we could do FOIL on k. We could do FOIL on k plus 2 times 2k plus 3, right? That's what we're trying to see if that equals that. So we could do FOIL. We'd have 2k squared plus 3k plus 4k plus 6. So that's going to be 2k squared plus 7k plus 6. And that's what that is, right? So I know that's what that factors into. So you can either do it by trial and error this way, or you can, if you have the skill, you feel comfortable with your skill, you can factor this just knowing, well, what do I multiply by, what can I multiply by 2, and what multiplies with, when you factor the 2 and the 6 and adds to be 7. If you remember your factoring. Anyway, so either way you do it, we're going to get, in the end, we get k plus 1 times k plus 2 times 2k plus 3 all over 6, and then the left equals the right. Right? And so we've proven it. That's a proof by math induction. All right. Questions? Use this example, that last example. You follow that example every time you do your homework till you get the process down. Follow that example. That's a sort of a guideline for how to do the induction proof. But it's a step-by-step process. You have to include every step. If you leave out steps, you'll get deducted. Because the steps at the beginning are the most important. Where you do the P1, that's a point. If I were grading this, P1 would be a point. I'd give you a point for changing everything to K. That's an easy point. Then I do the point where you plug in K plus 1. And then I give you a point for the induction step. Right? So there's 4 points right there. And then all the other work, doing all the other work, I probably give you a point for doing the left side right correctly and then doing the right side correctly. Simplifying both of those, and you get your point. So a lot of the work, is you get points for the steps, not necessarily all the work. All right. Okay. I think I need to do. Let me stop this here.